Recording is rolling. It is Friday, November 22nd. Today's gonna be a lab day, Inelastic Collisions Lab. You guys have this lab page in front of you right here. All right, so I'll show you guys what that's about here in a minute, but here's some other agenda stuff. I know last few days there's been a lot of focus on this in-class quiz. So just to recap, but you guys took this on Wednesday, and then we did a redo on Thursday, and I went over in class, step by step how to solve these. All right, so anyway, if you either have not taken this quiz at all, or you only took it the first day, because the redo, everybody got a much better score, right? And you want to do the makeup today in class, let me know, and I will put this quiz in your hand. You can open your laptop and open up yesterday's video, which is on Google Classroom, and go step through step, exactly like we did in class yesterday. So if you want that, let me know. I'll get that to you. All right, since I'm doing a recording for all my classes, my AP students, I did open up some FRQs on AP Classroom. Not that I'm gonna score those, but if you want some extra practice or see some extra questions, there you go. All right, yeah, and we're going to Thanksgiving. I think it's a good way to go into Thanksgiving. So we're kickstarting a new topic. So I want to introduce these ideas so that when you guys come back from Thanksgiving break, you will have seen this a couple of days, and it'll make this stuff make that much easier to learn. All right, so we're looking at this property in physics called momentum. Momentum. So this letter P, guys, what does this letter P stand for? Momentum. Momentum. It's just very simply mass times velocity. How massive, how fast is it going, but also what direction. Because momentum, guys, is momentum going to be a scalar or a vector quantity? A vector. A vector value. And it's conserved, kind of like energy was conserved. So you can set up a conservation equation. Conservation equation for what? What scenario? Collisions. Whenever you see a collision, you probably want to use this particular method. All right, so you guys are going to see a lot of collisions in the next few weeks because that's and this thing. Right. Now your lab today, we're going to focus on a special kind of collision called perfectly inelastic. On your lab paper, guys, lab paper. There's two sides to it. We're only going to do the side that says perfectly inelastic. You guys see perfectly inelastic right there? Okay. So let's look at this perfectly inelastic poster. We got these covered up. I'll show you guys why in a minute. But here's in general what's going on. So yeah, got two objects headed toward each other. You guys are going to get these carts on the low friction tracks today. And they could collide, right? So got a collision going on. And then what? Well, then what depends on a lot of things. What kind of collision? Do they bounce off each other? Boing, like Newton's cradle balls? Could they like kind of half bounce off each other, like half deflated balls? Could they stick together? If they stick together, that's called perfectly inelastic. You guys see I taped some magnets on here? Got some magnets with some paper towel pads. So it goes, pow, right? And then it's gonna stick together. Right, you guys see that? Sticks together? Right. Okay, well, that will make it perfectly inelastic then. You guys see that? Okay. Now here, guys, here's a little side thought. Is that somebody did ask earlier, hang on a minute, if there's magnets there, it wouldn't be true as one approaches the other, it kind of pulls it, and then they kind of accelerate towards each other. Yeah, a little bit, right? But since that's just internal to the two object system, it's just internal. So in the big scheme of things, it doesn't really make a difference. So we're just gonna not worry about that. Right. So if I add up all the mass velocity bits before the collision, and I add up all the mass velocity after the collision, it should equate. And notice if it's perfectly inelastic, then you have one giant mass moving at a common final velocity. Does that make sense? What this equation? If momentum is conserved. Right. Let's do an example. Right, suppose this is coming in from left to right with like 10 units of momentum to the right. And what if you have this one coming with 10 units of momentum to the left? Guys, what is 10 units to the right and then negative 10 to the left? What is the total momentum equal to? Can anybody do that? Okay, somebody do that. What is 10 plus negative 10? 0. So does that mean there's 0 momentum in the system? Yes, that's what that means. Right. Hold on a minute. That sounds a lot different than energy. Because if you did 1/2 mv squared for kinetic energy, this could have a lot of energy, and this could have a lot of energy. Yeah, because energy was a scalar. This is a vector. That's why it's different. Right. So, and I bet if you had exactly that, like 10 versus negative 10, I bet it would just come to a dead stop, probably. Right. You think? Because that would also show 0 momentum. That would be consistent, wouldn't it? Is that? Right. Now, this particular lab, we're going to simplify this even a little bit easier than what you guys are looking at right here. You guys are going to start cart B at rest. So you guys see this VB right here? What is the initial value equal to? Did I just say? 0. That's right. So I'm going to cover it up just to really emphasize that there is no velocity. It's just sitting there. Da-di-da-di-da. It's just mind its own business. And then down here, does this also go to 0? So I'm going to cover that up. Okay. This is all you need today. Like I said, so you're gonna have one card that's rolling, one card that starts out stationary, they're gonna collide, bam, and then they're gonna slide off together, right? And the momentum, mass, and velocity to start with before the collision should equate to after the collision. Make sense? Okay, hopefully, or you're gonna test that out. That's what you're trying to test out. So you guys got one card at rest, one card's rolling. Right? Now, if you have an empty card, suppose you don't have anything on it, an empty card. Take a guess. How many grams mass do you think is this card? 500. So an empty cart could be 500 grams. Right. Now there are a bunch of lab weights back there. Suppose I take 1,000 grams and plunk. Guys, what is this 1,000 plus this 500? What is that? It'd be 1,500 grams, wouldn't it? You could also call it 1.5 kilograms if you want to record it in kilograms. Okay. Right. So guys, here's basically all you're doing. Right. This one starts at rest. This one comes in rolling. Bam, and then they roll off together. Okay. Right. Like that. All right. So let's look at this lab table. Because there's different ways to do this lab. There's different procedures. And I'm going to leave this a little bit open to you guys. And depending on which procedure you do, actually, the numbers work out a little different, but I'll come in about halfway through class and I'll fill you guys in on that detail, right? There you go. So do you guys see this, how this is organized? I got pre-collision on the left. I got post-collision on the right. You see that? So you can have one giant row going across. Like that entire row could be one trial. Right? So my left hand is like leading into the collision, and my right hand is after the collision, after they're stuck together. Right? And what you're comparing are these two boxes right here. What's this momentum compared to this momentum? And it should be the same. That would show conservation momentum. Is that true? You set? Right. Then these boxes down at the bottom is you can just copy paste this or just not write it all. It doesn't matter. Okay. Guys, this and this is this and this. I just made it bigger because some of these numbers might be kind of big. Why would they be kind of big? Because do you guys see for units I put grams and centimeters? Do you guys see that? Right. So guys, if you do grams and centimeters, I'll tell you what these numbers are going to be. They're going to be like maybe 10,000, 20,000, something like that. Grams, centimeter per second. Right. If you don't like big numbers, because some students said, I don't know, these numbers are really big. Could you convert grams into kilograms? And if you wanted to, could you convert centimeters into meters? Right. Suppose you did that. Okay, going from grams to kilograms. How many decimal places is that? 3. Factor of 1,000. Going from centimeters to meters. How many decimal places is that? 2. Right. So if you want to keep exactly what I have, you can do that. You're going to get numbers in the probably 10 or 20,000. If you want to roll back 3 decimal places, you could change the mass to kilograms. If you only want to roll back 2 decimal places, you could change centimeters to meters. And what if you change both? What if you have kilograms and meters? That's how many decimal places altogether? 5. So I'll leave that up to you, how you want to record it, as long as you're comparing apples to apples. Okay. All right. So here, I'm kind of starting from the end because I'm explaining this backwards. So you're leading up into trying to figure out what's the momentum before and after, and does that relate? Right. You guys see here I have a place to record the masses, right? Mass A, mass B, right? And here's mass A plus B because it's combined after the collision. Right? So good. Okay. And then if only you have the velocities before and after, then you could calculate the momentum, because momentum is not some velocity. So here I have velocity before and after. Now notice for part B, I already zeroed out for you guys before the collision because it starts from rest. You guys see that? Why that number would be 0? Starting from rest? Okay. Okay, so what's the velocity of A, and then what's the velocity of A and B together after collision? You see it? Okay, now here's where maybe different procedures could diverge. And I'm going to leave it up to you guys how you want to do this. So one way you could get these velocities is this. You could take, I've got some plastic markers back there. So this might be set up from before. And some masking tape. You could set up like a vertical marker here. Pretend this is a marker. And you have some speed gates. And you could run this through a speed gate. Yeah. And you could measure that number directly. How fast is this rolling? Yeah. You guys can do that? Right? Alternative. Okay, sorry. And if you do that, you don't need distance or time at all, right? The other way you could do it is you could measure, well, how far does this go and how much time with the stopwatch? And then you would need these columns. So how far does it roll and how much time? And then if you know how far and how much time, could you calculate how fast it's going? So you guys could do that too? You see that? All right. Right. So let me repeat what I just said. There's two different ways to get the velocity. You can measure it directly with the speed gate, or you could say how far does it roll and how much time, and then you could divide those and calculate how fast it's going. You guys get that? Right. All right. So good so far? Right. All right. And remember, your end goal is compare these two momentum and see if they're the same thing. Right. Now, I'm going to throw one more idea at you guys before I send you back there, which is that depending on how you do this lab, you might get numbers that are pretty close to each other, which would be good. Right. Or here's a really common thing that I've seen year after year, and even earlier today through multiple teams. You might get the final momentum is approximately half of the original momentum. Like if the original momentum was like 30,000 units, the final momentum might be really close to 15,000. Right? And if you do, there's a specific reason why. In fact, if I look at your lab paper and I see that, there's something I know that you did in your procedure to get to that point. So I'm curious to see how you guys do your procedure. And if you do, then I would know pretty much why that would be. So I'm going to come in about 20 minutes and I'll show you guys what would lead to that if you got that. But right now it's a little bit information overload. I think I told you as much as I can tell you for now anyway. So go ahead back to the lab area, get all the lab data you need. Again, if you need that in-class quiz, let me know. I could get that to you. All right, so I'm going to leave this up here. And I'll come in about 20 minutes to give you guys a little more info. All right, so that's a good pause point right there.
Get that